NASA's James Webb Telescope has demonstrated its exceptional capability to investigate the atmosphere of a massive exoplanet located more than 1,000 light-years away. This achievement represents a significant milestone in astronomical research, bringing to fruition a long-held dream for astronomers. Webb's latest findings include the discovery of haze clouds and ambiguous water signatures in a single observation. These results were made possible by the telescope's powerful combination of a 270-square-foot mirror, precision spectrographs, and highly sensitive detectors. The ability to make these discoveries is a remarkable advancement, especially considering that similar observations were once deemed impossible with previous technology. Webb utilized its near-infrared imager and slitless spectrograph to create the transmission spectrum of the hot gas giant WASP 96b. This observation provides only a glimpse into the exciting future of exoplanet exploration that Webb promises. As detailed in the latest episode, a distant exoplanet's steamy atmosphere has been unveiled by Webb. The telescope successfully captured the water vapor signature in the atmosphere of this hot, puffy gas giant, which orbits a sun-like star far from our own solar system. Alongside detecting water vapor, Webb also identified signs of clouds and haze in the exoplanet's atmosphere. The observation of WASP 96b is noted as the most thorough of its kind to date, showcasing Webb's extraordinary ability to study atmospheric conditions on planets thousands of light-years away. The data collected involved measuring slight reductions in the brightness of specific colors of light, which indicated the presence of various gas molecules. While the Hubble Space Telescope has contributed to our understanding of exoplanet atmospheres over the past 2 decades, detecting water for the first time in 2013, Webb's rapid and comprehensive observations mark a major advancement in identifying potentially habitable planets beyond Earth. The Milky Way is home to over 5,000 confirmed exoplanets, including WASP 96b. This exoplanet represents a type of gas giant that does not have a direct counterpart in our solar system. It resides approximately 1,150 light-years away in the constellation Phoenix, situated in the southern sky. WASP 96b is notably puffier compared to any planets orbiting our Sun, with a mass less than half that of Jupiter and a diameter that is 1 or 2 times greater. Its temperature is extremely high, exceeding 1,000 degrees Fahrenheit. WASP 96b completes one orbit around its Sun-like star every 3.5 Earth days, with its proximity to the star being just 1/9 the distance between Mercury and the Sun. This close orbit makes WASP 96b an ideal target for atmospheric studies due to its large size, short orbital period, puffy atmosphere, and the absence of interfering light from nearby stars. On June 21, Webb's near-infrared imager and slitless spectrograph observed the WASP 96 system for a duration of 6.4 hours as the planet transited across the star. The resulting light curve illustrates the overall dimming of starlight during the transit, while the transmission spectrum reveals variations in brightness across specific infrared light wavelengths ranging from 0.6 to 2.8 microns. This detailed transmission spectrum uncovers previously unknown aspects of WASP 96b's atmosphere. In contrast, the light curve serves to confirm the planet's previously established properties, such as its existence, size, and orbital characteristics. The detection of water and the presence of haze and clouds were unexpected findings, given earlier observations that suggested these features might not exist. The process of creating a transmission spectrum involves comparing the starlight filtered by the planet's atmosphere during a transit with the unfiltered starlight observed when the planet is adjacent to the star. By analyzing the absorption patterns, scientists can determine the locations, heights, and peaks on the spectrum graph, which helps identify and quantify the abundance of critical gases in the planet's atmosphere. Atoms and molecules exhibit unique wavelength absorption patterns, akin to how people have distinct fingerprints and DNA sequences. The spectrum of WASP 96b, captured by Webb's near-infrared imager and slitless spectrograph, NIRSS, not only provides the most accurate near-infrared transmission spectrum of an exoplanet atmosphere to date, but also spans an impressive range of wavelengths, including visible red light and regions of the spectrum previously inaccessible from other telescopes. Essential molecules such as water, oxygen, methane, and carbon dioxide, though not immediately apparent in the WASP-96b spectrum, are particularly sensitive to this newly accessible portion of the spectrum. Researchers are now equipped to measure the amount of water vapor in the atmosphere, constrain the abundance of various elements like carbon and oxygen, and estimate the atmospheric temperature at different depths. This information is vital for understanding the planet's overall composition, formation history, and potential habitability. The best fit model, represented by the blue line on the graph, integrates the data with known characteristics of WASP-96b and its star, as well as the hypothesized properties of the atmosphere. Advances in Webb design and technology have significantly enhanced the clarity and detail of these measurements. Webb's 270-square-foot gold-plated mirror effectively captures infrared light, while its sensitive detectors detect minute brightness variations. Its precise spectrographs disperse light into a spectrum of thousands of infrared colors. NIRS is capable of distinguishing brightness differences between colors that are just a few hundred parts per million apart and color differences as small as a few thousandths of a micron. It covers a range of infrared light wavelengths previously inaccessible, which is particularly exciting for researchers. Although other telescopes have studied the infrared atmospheres of exoplanets, none have matched Webb's level of detail. This represents only a fraction of the data collected. Colin, an expert on exoplanets, highlights that Webb's extreme stability, its orbital position around Lagrange 2, and its distance of approximately 1 million miles from Earth's atmosphere enable uninterrupted observations and rapid data analysis. The incredibly detailed spectrum, achieved by analyzing 280 individual spectra simultaneously, provides only a glimpse of what Webb will contribute to exoplanet research. In the coming years, researchers plan to use spectrography to examine the atmospheres of numerous exoplanets, ranging from small rocky planets to giants rich in gas and ice. Exoplanet research constitutes nearly a quarter of JWST's observing cycle in a single observation. This closest observation underscores Webb's ability to characterize exoplanet atmospheres, including those that might be habitable. Antonella Noda, a JWST scientist overseeing the European Space Agency's office at the Space Telescope Science Institute, notes that much of the science will be conducted using spectra. While a picture is often said to be worth 1,000 words, astronomers consider spectra to be worth 1,000 pictures. As today's episode concludes, we eagerly anticipate that the James Webb Space Telescope's enigmatic discoveries will continue to provide us with new and surprising insights into exoplanets. If you enjoyed the content, please give us a thumbs up and subscribe to our channel. I look forward to seeing you in the next episode.